Well, hello, my name is Sara Zapata. My supervisor is Dr. Alexandra Schmidt from the Department of Epidemiology, Biostatistics, and Occupational Health. And today I will be talking about one of my projects, which is the spatial modeling of ambient VOCs in Montreal. So the outline for this presentation is that first I will give a brief introduction on what are VOCs and why is it important to study them. Then I will talk about the data and the objectives that we have for this project, the methods that we follow, the predicted surfaces, our conclusions, and some strengths and limitations from this type of models. So first of all, what are volatile organic compounds? So VOCs are organic chemicals that have high vapor pressure and become gases at ambient pressure and temperatures. And why is it important to study them? Well, it has been estimated that annually around 19% of all, it has been estimated that around 19% of all cancers are attributable to environmental factors, and around 4.2 million people die of diseases that are exacerbated by air pollution like strokes or lung diseases. And then the World Health Organization says that around 99% of the world's population, so almost everyone, lives in a place with poorer quality, especially in low and middle income countries where they suffer from higher exposures. So what is the context of VOCs here in Canada? So this is data from Canada's air pollutant emissions inventory from 2021. And I am showing data from 2005 because that was the year when our data was collected. So in 2005, the oil and gas industries were the main sources of VOCs, accounting for around 29% of the emissions, followed by transportation and mobile equipment with 27%, and paints and solvents with 19%. And in that year, 2.3 megatons of VOCs were released in Canada, but from 1990 to 2005, there was a 21% decrease in VOCs emissions, mainly because of some new regulations. So for this study, we analyzed 5 VOCs. 3 of them are aromatic hydrocarbons, so benzene, ethylbenzene, and trimethylbenzene, and 2 of them are alkane hydrocarbons, so decane and hexane. From these 5, benzene is a known carcinogen, and ethylbenzene is suspected to be carcinogen for humans. And we are analyzing these 5 VOCs because all of them are constituents of fossil fuels. So we have a 2-week period sampling of these 5 VOCs for 3 monitoring campaigns. So the first monitoring campaign was during December 2005 to account for the cold weather, April 2006 to account for moderate weather, and August 2006 for hot weather. And these little badges were placed at the different monitoring locations, and then they collected them and they sent them to a laboratory to be analyzed. And as our coverage, we used data on land use variables like open areas, residential areas, industrial, and roads, average and total nitrogen oxides, total daily traffic volume, and population density. So for the monitoring network, my collaborators deployed the monitors using a population-weighted location allocation model that would place the samples in areas with high spatial variability of traffic-related pollution and in areas with high population densities. And additional to that, there were also another 30 monitors that were placed in residential areas that were originally underrepresented by the location allocation model. And since the primarily focus of this study were residential areas, there were no monitors placed in the around the airport and in the north part of Montreal. And later on, I will show you how this affects our predicted surface. So for December and April, there were in total 133 monitoring locations. And for August, there were 131. So the two main goals for this project were first to determine the spatial variation of ambient concentrations using land use regression and geostatistical methods. So land use regression is just the standard method for this type of data, and it's just a regression method that is used to describe the relationship between sample locations and environmental variables. And the second objective was to develop predicted surfaces to link with residential addresses of participants in cancer control studies. So we have data on the addresses of patients with prostate cancer and breast cancer from the early 2000s, and to estimate the risks associated with exposures to these VOCs. So this is our base model. So for all of the VOCs, we are modeling the concentration in the log scale. So here YJS is the log concentration of a VOC at campaign J, where J is the campaign, so December, April, or August, and at location S. The first term contains an indicator variable that represents each campaign, and alpha is the coefficient that is associated with that indicator variable, so it captures the campaign effect. X contains all the land use variables at location S. The coefficient that is associated with those land use variables can change across campaigns, so it would be a beta J. And then our measurement error follows a normal distribution with mean 0 and variance tau square. Tau square is the variance of the non-spatial effect or the nugget effect. And we also consider a latent spatial structure, so omega j, and this follows a multivariate normal distribution with mean 0 and an exponential covariance structure, where sigma square is the spatial effect variance, and this function is, the covariance function depends on the distance between the sites, so our matrix D, and the spatial range that is related to the distance beyond which the association between sites becomes negligible. So for all of the VOCs, we fitted 4 different variations of this base model. So in model 1, we are considering that the first term captures all the across campaigns variability, but the coefficients associated with the land use variables are constant, and we have our latent spatial structure. And model 2 is similar to model 1, but in this case, we don't have a latent spatial structure. So we are saying that all the spatial variability has already been accounted for by the land use variables. And then in model 3, we allow the coefficient associated with the land use variables to change across campaigns so that all the spatial and across campaigns variability is being captured by this term. And we also have our latent spatial structure, and model 4 is similar to model 3, but in this case, there is no additional spatial structure. So everything is already being captured by those land use variables. So because we are following the Bayesian paradigm, the model specification is only complete after we assign a prior distribution to the parameter vector for each model. Because we don't have enough information on how the relationship between the VOC's concentration and the land use variables is, then we assign non-informative priors for the coefficients alpha and beta in model 1 and 2. So they follow a normal distribution with 0 mean and a relatively large variance. And then for models 3 and 4, where we are allowing the coefficients to change across campaigns, the prior follows a hierarchical structure in the mean and variance. And when we have a latent spatial structure, the priors for the non-spatial, for the partial seal and the nugget effect follow also an inverse gamma prior with a mean fixed at 1 and an infinite variance. And finally, for the spatial range, we assign an exponential prior with its mean equal to practical range, which is the value when we assume that the correlation between sites decreases to 0.05 at half of the maximum distance. So for all the fitted models, the resultant posterior distribution does not have a closed form. So we followed MCMC methods, and all the models were implemented using Nimble in R. So once that we have implemented all the models for all of the VOCs, we chose the best model for each VOC using WAC, which is a Watanabe-Akaike information criterion, and it accounts for the goodness of fit and the model complexity. So the best model among the fitted ones for benzene and decane was model 1, in which we assume that the coefficient associated with the land use variables is constant, and we have our latent spatial structure. And then for ethylbenzene, hexane, and trimethylbenzene, the best model among the fitted ones was model 4, in which we allow the coefficients associated with the land use variables to change across campaigns, but we don't have an additional spatial structure. So because we're interested on obtaining our predicted surfaces, so we want to predict the VOCs concentrations at unobserved locations, so that's YUJ, using information on the concentration at the observed locations YJ. So the joint distribution of the VOCs concentrations at the unobserved locations and at the observed locations follows a multivariate normal distribution with mean mu UJ for the unobserved location of locations, mu J for the observed locations. And here the matrix sigma UJ is the covariance matrix among the unobserved sites. Sigma J is the covariance matrix among the observed sites. And psi is the covariance matrix among the unobserved and observed sites. So following the properties of the multivariate normal distribution, the marginal distribution of the VOCs concentration at the unobserved sites, given the VOCs concentrations at the observed sites, and the corresponding parameter vector according to the model that we found before, follows this distribution. But for models 2 and 4, where we don't have an additional spatial structure, the distribution is just reduced to this normal distribution, where now sigma is a diagonal matrix because there is no relationship between the unobserved sites or between the observed and the unobserved sites. So these are our predicted surfaces for each of the VOCs. So for all of them, we found higher concentrations during the December campaign. And for benzene, it was interesting that we found higher concentrations in the northeast part of the island for all 3 campaigns. And that is because there were some refineries that were operating at the time when the study was done. And I think they closed after 2008. So in general, in August, we found lower concentrations, but still there is a hotspot in the northeast and in some of the highways. And then for decane, again, we found higher concentrations during December, but here we found higher concentrations in some of the highways this is December. And then for April, there's also a hotspot around the Ville de Montreal. And for August, in general, also lower concentrations, but there are still like hotspots in some of the highways. For ethylbenzene, we found higher concentrations in all the east part during the December campaign. We found higher concentrations around the mountain for the April campaign. And in August, we found higher concentrations here in the southeast. And then, and I should point out that these predicted surfaces are showing that there is a lower concentration in the airport, but that is because there were no monitors there. So later I will show you our uncertainty map. So hexane, sorry, there. Hexane was the most abundant ones of all the VOCs. So for April, again, we found some hotspots in some of the intersections of some highways. And again, it's showing lower concentrations in the airport, but from the lack of monitoring locations there. And then trimethylbenzene was the one that showed like higher concentrations in almost all of the major highways and around the mountain area. So this is for December. Then April, again, there is a hotspot here around the Petite Patrie area. And August, there were also higher concentrations here in autoroute 15 and in some of the autoroute 40. So this is our, okay, so on the upper panel, I am showing the posterior mean of the, for the end decane. And in the lower panel, I am showing the posterior standard deviation to show our uncertainty. So this is what I was talking about. Because we don't have any sites there, our uncertainties in that area are actually higher. So that's why you should also look at the uncertainties. So some conclusions from this project is first that we found higher concentrations during the December campaign. And this has been found also in other studies in other cities. This is due because there sometimes are like weather conditions that can help trap emissions for a longer time. Also from cold starts from engines and from home heating. And then for benzene, the highest levels were predicted in an area where the oil refineries were operating at the time of the study. For decane, highest levels were predicted for sections of autoroute 40. And for trimethylbenzene, it showed higher levels in almost all of the major highways. And okay, finally, some strengths and some limitations of this type of modeling and land use regression in general is that first, it can help to identify hotspots or to define at-risk groups. It can also help to show changes in spatial patterns of pollutions, like also for after some like new regulations enter. And it can be easily adapted to local circumstances and data availability. But some of the limitations is that it is really case and area specific. So there has been some papers that have tried to transfer models from one city to another one with a similar geography, but in general, they haven't succeeded. Also, the number of monitoring sites can affect the relationship found with local factors. And I think one of the main problems is that there is no consensus on the monitoring process. So there is no consensus on how many monitors should you have, what the sampling period should be, or the distance between the monitoring locations. So thanks. I would just like to thank Mark Goldberg for allowing me to work with this project, my supervisor, Alexandra Schmidt, Dan, Marianne, and Jat for providing me with the data, Dr. Eric Levin, and my sponsors. Thank you.
Thank you very much, Sarah. Some questions for Sarah. We have one from Simon.
Yes. So actually, I had two. One is, will the data, the predicted data be available, like for, researchers studying different populations in Montreal, perhaps by zip code or something like that? And the other one, oh, go ahead.
Sorry, I think so, but right now, Mark is working on using this data for the cancer studies. So I don't know when it would be available.
And then in Montreal interest, so there were a couple of pollutants that had this ring around the mountain, and in particular, they were very present in the McGill Plateau area, even though there is no highway there particularly. So do you have an interpretation for what's going on there?
No, but I am assuming because everything is related almost like to traffic, that there might be like a lot of traffic going on around this area.
Rodrigo.
Hi, very nice. Sorry, I wanted to ask two things. So I know that this analysis is spatial dependent, so you cannot really directly do the same thing in other places and translate what you would see. But just to have an idea of, at the beginning, the statistics that you gave us about Montreal, how does that compare to other cities, or how can you have an idea of like comparison between those? And the other thing that I wanted to ask is, what does the fact that different compounds were best fitted with different models tell you about them? So what does it mean that you needed model 4 for the last 3 and model 1 for the first one? Does that have any interpretation of what would that come to be in terms of, is it related? Yeah, you got it. You understood what I mean.
Okay, so about the first question, it is really interesting because from what I have read, all this is really like city specific. So for example, there was one study that compared cities between the USA and Canada. And in the USA, the factors that contributed more for the VOCs emissions were traffic. And in Canada, it was the number of chimneys in the area. So it was coming from home heating. So that's one of the things that it's really specific. One thing that we found interesting is that everyone, and it's because of how it works, but that everyone found higher concentrations during winter periods in many different cities in the world. And then for the second part, yes, okay. So in our case, for example, the latent spatial structure is captured anything from like the spatial structure that is left after accounting for the land use variables. So what it might be happening is that we don't have exactly the land use variables that would be explaining the variation of these two VOCs. And that is being captured by what is left in the spatial structure. So it might be that we are lacking information that of some land use variable or some spatial variable that is affecting the concentration of these VOCs. If you are talking, you're mute.
You're muted, Rodrigo, yes.
So that would explain why the last three were not properly fitted with the first one. Is that what you're saying? Or did I get it the other way?
I mean, for the last three, there was no additional spatial structure. So it might be that like the majority of, well, that they were related more to traffic, for example, that is accounted for by the land use variables here. So there's no spatial structure left after using those land use variables.
So it could be something that's similar to the chimneys versus traffic thing, for example, because that won't change. Okay, that's it. Thank you.
I think we'll take one last question and then we'll give everybody a short break before the next set. So we have a question from Bianca about wind. How does wind change results?
Yes, because this was, I mean, the way that this was done is that they just left the monitors for 2 weeks and then they came back for them. There has been some studies that now are trying to incorporate like weather conditions into these type of models, but the problem is that, I mean, weather changes a lot from what I saw from, for example, the Pollen project. I mean, the weather changes a lot from 1 week to another. So if I leave the monitors during 2 weeks, the conditions are going to be really different in that period.
Thank you very much, Sarah. I'd like to thank all the presenters. I would like to also point out that the 3 presenters you just heard have expressed their intention to graduate